All right, welcome everybody and good afternoon and welcome to my webinar here. As Chris said, it's titled Inside the Envelope, Modern Ductwork Strategies for Energy Efficient PA Homes. Here is the description. As you probably already read when you registered for it, we'll briefly review common approaches like soffits, drop ceilings, and unvented attics, along with newer system options as well. So we'll be touching on anything ductwork related throughout this presentation. Again, these are the learning objectives for the webinar that will be incorporated throughout the presentation. So with that said, we shall begin. Before I continue, I just want to clarify that this presentation is educational in nature. I'm not promoting any specific product or method. It's important that systems and materials are selected based on the needs of the designed assembly. So where are your ducts located within the home? Inside the thermal envelope or outside of it? That's one decision that has a major impact on energy use, comfort, and whether you meet codes. So as we go through this webinar, we're going to connect that idea to the thermal boundary, air barrier, code requirements, and some testing as well, as we're going to show why duct locations truly do matter. So as we begin, I want to clearly define what the meaning of the building thermal envelope is. The thermal envelope is the continuous boundary that separates conditioned space from unconditioned space. It includes the insulation layer and the air barrier system working together to control the heat flow and air movement. It's important to distinguish between the thermal boundary and the air barrier, although ideally they do align and they are continuous, typically. The thermal boundary is defined by the insulation. It resists conductive heat transfer, where the air barrier controls air leakage, preventing uncontrolled infiltration and exfiltration. When those two layers are misaligned or they're discontinuous, we can create pathways for energy loss, moisture migration, and potential durability issues as well. So now let's relate this directly to ductwork placement. When ducts are installed inside the envelope, they are located interior to both the insulation layer and the air barrier. In this configuration, any minor leakage or conductive loss remains within conditioned space. Now, in contrast, when ducts are installed outside that envelope, such as in vented attics, vented crawl spaces, or any space beyond that air barrier, they are exposed to extreme temperature differentials. As we all know in Pennsylvania's climate, that means hot, humid summers or cold, brutal winters as well. The diagram on the right on the slide, it illustrates the continuous thermal envelope wrapping the conditioned portion of the home, as you see in the dark brown or the brown layer there. Anything outside that highlighted boundary is considered unconditioned space. As we move through this webinar, keep this boundary concept in mind because duct location relative to the thermal and air control layers fundamentally determines the system efficiency, the comfort, and the overall building performance. So in continuation with our discussion on why duct locations matter, let's consider our ductwork is located outside the building thermal envelope. In spaces like those vented attics or crawl spaces, we introduce avoidable losses. So duct losses, that's any heating or cooling delivered into those spaces, the energy that never makes it to the living area, it gets lost. That leads to higher energy use. It could lead to longer run times or increased operating costs as well. It also shows up as comfort issues. Rooms that are too hot or too cold and can introduce moisture risks, especially in a mixed humid climate like we have here in PA, condensation becomes a concern. So duct leakage, even small amounts have huge impacts. When ducts are outside the envelope, that air is often lost directly to the exterior, which reduces system efficiency and it undermines the performance of an otherwise well-designed enclosure. So when looking at the goal, it's pretty straightforward. We want to keep energy where it belongs inside the home. We want to improve comfort and durability, and from a code standpoint, we want to simplify compliance. So the most effective way to achieve all of that is simple in concept. It's locate the ducts inside the conditioned space whenever possible. I always think back to when I was a kid, my parents would always yell, "We're not heating the outdoors. Close the window or close the door." It's kind of the same concept. So looking ahead here, traditionally ductwork is installed in areas like vented attics, unconditioned basements, and garages, spaces that are outside the thermal envelope. I know I've seen it a lot in a lot of homes that I've been in. So keep in mind when ducts are located in those areas, they're being exposed to those extreme temperatures, which is leading to energy loss. In the winter, heat is lost, and in the summer, heat is gained, making the system work harder. And it can also create condensation issues, increasing the risk of moisture problems and long-term durability issues as well. So looking at some codes here in PA and what Pennsylvania requires, residential construction follows the Uniform Construction Code, or the UCC, which is based on the 2021 IRC and IECC. So as I have shown here, the 2021, mostly the Chapter 11 out of the IRC, the International Residential Code, and then the IECC, it's the residential provisions. So that's the International Energy Conservation Code. Along with that, those codes, those are the model codes that we use, but then they can be or they are modified in some aspects by the PA specific amendments through our RAC, which is our Review and Advisory Council. They create amendments along with, we also have a Pennsylvania Alternative Residential Energy Provisions, the PA ALT, which is called the 2025 PA ALT. And for future reference too, they are links. I created links there for the RAC amendments and a link to the PA ALT as well, if you are interested. And there's a link for PA ALT related files, a direct download. So moving along with those codes, there are base codes that we start with. So I'm going to talk or touch base on some of the codes that relate to ductwork. This section of the code addresses duct insulation when ducts are located outside the conditioned space. The text you see on the screen is direct code language that I pulled from the ICC. I've highlighted where it addresses the R values, and what it states is supply and return ducts must be insulated to at least an R8 for ducts 3 inches and larger, and an R6 for ducts smaller than 3 inches. The intent here is to reduce energy loss when ducts are exposed to conditioned environments. However, even with insulation, ducts outside the envelope can still experience performance losses. This is why bringing ducts inside that conditioned space is the preferred approach when possible. So moving along, let's define what qualifies as ductwork being located inside conditioned space. This is also direct language that I pulled from section N1103.3.2. And it states in here that for ducts to be considered inside the envelope, they must be fully within the continuous air barrier and the building thermal envelope. So this is important because simply placing ducts in a floor or a wall cavity does not automatically mean they are inside conditioned space. The enclosure must be continuous and properly sealed. The image that I have on the screen, it's a good example of this concept. It illustrates ductwork installed within a floor system where insulation and air sealing are used to separate the duct from the unconditioned space below, which is most likely it could be an unconditioned basement. And it's keeping it within the conditioned envelope. So that's within the conditioned space. So when this is done correctly, this approach helps reduce that energy loss. It also improves system performance, and it can eliminate the need for certain duct insulation and testing requirements. Some more code language that I pulled. This is N1103.3.2 as well. In this section of the code, it outlines an exception where ductwork can be located in a ventilated attic and still be considered within the conditioned space if specific conditions are met. So as it notes there first in 2.1, It states the air handler must be fully inside the thermal envelope and air barrier. And then second is in 2.2, it notes that the system must meet very tight duct leakage requirements, significantly lower than standard allowances. This ensures minimal loss to the outside. And then the third one in 2.3, it states the ducts must be buried within ceiling insulation, and the insulation above the duct must maintain the required R value for the ceiling assembly. So the important point here is that simply placing ducts in an attic is not enough. This is a high performance approach that requires proper design, installation, and verification to meet code and perform effectively. Some more code language. This is a continuation of the N1103.3.2 as well. This one addresses ductwork located in floor cavities and exterior walls. So looking at items 3.1 through 3.3, under number 3, when ducts are in floor cavities over unconditioned space, what it states here is a continuous air barrier must separate the duct from the unconditioned space. Insulation must meet code requirements as shown in section, so it references section N1102.2.7. And then also a minimum of R19 insulation is required between the duct and the unconditioned space. Then when you're looking at the items under number 4, you have 4.1 to 4.3. These are for ducts located in exterior walls. So with that, in 4.1, it states a continuous air barrier is required. And then secondly, a minimum of R10 insulation must separate the duct from the exterior sheathing. And then finally, the rest of the wall cavity must be fully insulated to the interior side. So it's important to understand that when ducts are placed in these locations, proper air sealing and insulation detailing are still very critical to keep them effectively inside the thermal envelope and performing as intended. Here I created, this is a table that I had developed, and where I found all this information is I pulled it directly from the IRC, IECC, and then I cross-referenced it with the Pennsylvania RAC amendments to ensure alignment with the UCC for Pennsylvania. As you can see, I have listed the general topic, followed with a code section for easier locating, as well as listed regulations and some field implications as well. On this table, I am highlighting key installation fundamentals, materials, connections, ceilings, or sealing, and support. These are the items that most directly impact system performance and code compliance in the field. As you can see on the table, for joints and seams, mechanical fastening is required before sealing. It's also important, tape, that is important to understand because tape alone is not permitted. So the connection must be structurally secure first, then sealed. And then if you notice under duct sealing, that stating all joints must be sealed using the UL 181 listed materials, typically mastic or approved tape. Traditionally, duct tape is not acceptable. I don't know if you've seen that in applications, but according to the code, duct tape is not acceptable. The main takeaway from this table should be that proper installation starts with solid mechanical connections, appropriate materials, and correct support. So when it's done correctly, you have a well-running overall system performance. Continuing with the reference table that I created, this section here addresses the focus on how insulation and duct location impact overall energy efficiency. Specific R values and requirements are here for reference, but the bigger picture is understanding that ducts outside the thermal envelope introduce energy loss. So for supply ducts, insulation requirements are typically R8 when located in unconditioned spaces. Return ducts have a slightly lower requirement, typically R6, but still must be insulated when outside the thermal envelope. Buried ducts, as noted here, are allowed, but they must meet specific criteria for insulation levels and installation. This is considered a stricter compliance path and must be done carefully to meet the code. And then duct location is another one that's a key design consideration. The IECC ties duct performance directly to the building thermal envelope under N1102 and N1103. So in all with these design decisions, especially where ducts are located, play a huge significant role in how well the system performs and how easily it meets code. So continuing on with that table, this part of the table pertains to duct leakage and performance verifications. So duct leakage testing is required under N1103.3.5 unless the system qualifies for an exemption. Testing is performed at 25 pascals using a duct blaster. Leakage limits are found under N1103.3.6. And then it states here the allowable leakage is less than or equal to 4 CFM per 100 square feet post-construction, or less than or equal to 3 CFM per 100 square feet at rough-in without the air handler installed. So testing is typically verified using a combination of blower door testing and duct testing equipment. And the last part of the table that I created here, this pretty much ties everything together by connecting the duct systems to the building envelope. Like the others, it was developed from the base codes as well. The thermal envelope defined under N1102 establishes what is considered conditioned versus unconditioned spaces, so you can find more information there. As you also see, I reference the areas that you will find in the code where it pertains to air sealing, attic configurations, as well as crawl spaces. It's important to review these areas and be sure you fully understand the importance of it and what it all means. So the main point here is that ductwork cannot be considered independent from the building envelope. Whether ducts are inside or outside the conditioned space affects insulation, leakage, and testing requirements. So ultimately, as I've stated already, good performance comes from aligning those HVAC designs with the building envelope from the start, not trying to correct it later if possible. Let's look now at some duct insulation requirements. And starting with the attics. In the attics, your ducts must be insulated to at least an R8 due to the extreme temperature conditions in those spaces. For other unconditioned areas, the requirement depends on the duct size. R6 for ducts smaller than 3 inches and R8 for ducts 3 inches and greater. However, there is an important exception note to note if ducts are located fully inside the thermal envelope, these insulation requirements may not apply. This reinforces the overall theme we've already discussed. Placing ducts inside the conditioned space can simplify compliance, and it can also improve the system, the overall system performance of the HVAC system. So let's look at requirements related to air handler leakage and testing. Air handlers are required to be airtight, meaning they must be designed to limit air leakage to a specified maximum level. This helps ensure that conditioned air is delivered efficiently throughout the system. To verify this, air handlers are tested using ASHRAE 193, which is the standard used to measure cabinet leakage as well. So what is important to understand is that the air handler is part of the overall duct system. So controlling leakage at the unit itself is just as important as sealing the ductwork for overall system performance. As we focus on duct sealing requirements, which are critical for overall system performance as well, it's key to note that all components of the system, including ducts, air handlers, and filter boxes, must be properly sealed to prevent air leakage. The materials used are also important. Only mastics, liquid sealants, tapes, fasteners that meet the UL 181 standards are permitted. This ensures durability and long-term performance. It's also important to note the distinction between materials. UL 181A applies to fiberglass duct systems, where UL 181B applies to metal and flex duct systems. It's important to understand and distinguish the difference between them. So overall, the proper sealing is one of the most effective ways to reduce leakage, and it also helps improve efficiency in the system. Let's take a look at the use of building cavities as ducts, which is something the code generally does not allow. However, the use of a wall or floor cavity as part of the duct system, just noting it can lead to air leakage, contamination, and poor system performance, which is typically why it's prohibited. But here in Pennsylvania, under the Pennsylvania RAC amendment, there is a limited allowance. It allows return air to be permitted in these building cavities as a duct. It's important to remember supply air is not permitted, just return air. The image illustrates on the slide how a cavity might be used as a return pathway, but it's important that it is done carefully and in accordance with the code requirements. And just remember, return air is permitted, but supply is not. Let's take a look at the two primary compliance paths available under the Energy Code, including how they relate to the Pennsylvania Alternative Residential Energy provisions. So first is the prescriptive path. This is where specific requirements must be met. This includes clearly defined criteria such as insulation values, equipment efficiencies, and importantly, they also set duct leakage limits. This path is more straightforward and is commonly used because it provides a direct checklist for compliance. The second option is your performance path. This can often be referred to as the ERI path as well. This approach allows for flexibility by permitting trade-offs between different components of the home, such as the building envelope, mechanical systems, and overall energy usage. So as the 2025 Pennsylvania Alternative Residential Energy Provisions, or we call it the PA-ALT, as that outlines this performance-based approach, it aligns the Pennsylvania's adoption framework by allowing compliance through modeled energy performance rather than strictly prescriptive measures. So, however, even with these trade-offs, duct leakage still can play a critical role. Poor duct performance can negatively impact the home's overall efficiency, and it can make it much more difficult to meet the required performance targets under that ERI path. So regardless of which path is selected, prescriptive or performance, it's important to understand that tight, well-installed duct systems are essential, and they directly do influence the overall system performance. So duct testing, duct leakage testing, let's dive a little bit into that. In these cases, testing is required to verify how much air is being lost from the system. There are two main types of testing. There's rough-in testing. This is done before the system is fully complete, typically with registers being sealed and sometimes with or without the air handler installed. And then you have post-construction testing, which evaluates the performance of the entire system once installation is complete. There are also specific prescriptive targets that must be met. These are measured in CFM per 100 square foot of conditioned floor area and vary slightly depending on the testing conditions. It's important to note that if the ducts and air handler are fully located within the thermal envelope, in some cases, testing may not be required. So overall, this process ensures the system is performing efficiently and it's meeting the code requirements as well. At this time, I would like to do a quick poll. I'm interested to see, let me see, I got to open it up here. How many of you are required to complete a manual J, manual S, or a manual D in your professions? Let's see, there we go. And you should see the poll on your screen. If you can click there, I'm seeing quite a few. None have been required. Quite a few manual J's, some manual S, some manual D's. Awesome. All right, so we're going to talk a little bit about them. So I'm going to continue on here. So some good testing practices is where they fall into place. When we begin with this, so it's under the ACCA, which is the Air Conditioning Contractors of America. Their fundamentals, they have the manual J form, which ensures we are calculating the correct heating and cooling loads for the home. The manual S form then uses those loads to properly size the equipment, avoiding issues like short cycling or poor performance. And then finally, the manual D form ensures the duct system is sized correctly to deliver the required airflow throughout the home. So for those of you that are saying that you've never been required, I should have created another poll because I'm curious to know if you've completed one, even though you weren't required. Back in the fall, I did a webinar on HVAC systems or heat pump options, and I talked about these manual J, S, and D forms and the importance of them. Because even with this, it's the proper design is crucial. Verification is also very critical. And that leads us into, from a testing standpoint, this helps us to make sure that we are installing the proper size ducts, the proper size equipment into the home. So, as I stated previously, ducts are tested at 25 pascals, which is the standard required by the IECC. Also, testing is performed at two stages. You have the rough-in and then you have final testing. And by doing these testing at different stages, you can catch issues earlier and then you can fix them and correct them for the final system performance test. It's also important to coordinate duct testing with blower door testing, since both contribute to overall air leakage in the home. And before you test, you want to verify that all duct connections are properly sealed using those approved materials, that UL 181 materials. And finally, beyond just passing a leakage test, you should confirm proper airflow and system balance to ensure the system performs as designed and delivers comfort to the homeowner. So along with all of those, moving on. All right, so for the second half of my webinar, we're going to start off with talking about some best practices and implementation with ductwork. So leading into that, focusing on what proper installation and air sealing look like in the field. First, using the correct sealing materials and techniques is critical. As I have stated multiple times already, we should be using the UL 181 listed mastics or tapes, not your traditional duct tape, and ensuring all joints, seams, and connections are properly sealed. Next is insulation continuity. It's important that duct insulation is installed without gaps, compressions, or voids, especially when ducts are outside that conditioned space. Breaks in insulation reduce effectiveness and can lead to energy loss as well. We also want to be aware of common field issues. So these can include properly sealed or poorly sealed connections. It could be disconnected ducts, compressed flex duct, or missing insulation. These are all things that can lead to failed inspections or poor system performance. So overall, proper installation and air sealing directly impacts the energy efficiency, the comfort, and the code compliance of the system. So let's take a look now at how we verify that the system meets both code requirements and performance expectations. First, we have blower door and duct leakage testing procedures. The blower door measures overall air leakage of the home, while the duct testing specifically evaluates leakage within the duct system. Both are important and often coordinated in or during the verification process. Next is interpreting the results for compliance. For duct leakage, we're typically looking at CFM per 100 square feet of conditioned floor area at 25 pascals. These results must meet the limits outlined in the IECC or PA energy provisions depending on your compliance path. And then finally, quality assurance documentation is critical. All test results should be properly recorded and submitted for inspection. This includes documenting test conditions, the results, and confirming whether the system passed or requires correction. Overall testing and verification ensures that what was designed and installed actually performs as it's intended to. And with all of that, as long as that's done, then we can tie it all together and we get the comfort code and coordination. First, maintaining comfort and quiet operation is the end goal of a properly designed and installed system. When the ducts are sealed, they're properly sized and located within the conditioned space, we reduce those drafts, the temperature swings, and any noise issues. It also makes for a happy client when you have all of those met. Next, as well, meeting and exceeding the code expectations is essential. That's what we all want. The energy code sets the minimum standard, but following best practices like your proper sealing, your insulation and testing, that helps ensure long-term performance and fewer callbacks as well. Finally, team collaboration is key to achieving durable systems. Having designers, builders, HVAC contractors, code officials, they all play a role in making sure the system is installed correctly and performs as it's intended to. So when all of them align, when your design, your installation, and your verification, they all align and they all work together, we get systems that are efficient, durable, and they deliver the true and real comfort that our clients are looking for. So along with that, let's look at some of the most common and practical approaches for bringing that ductwork inside the conditioned space. One common method here is using drop ceilings and soffits. These allow ducts to be routed within the building envelope while maintaining a continuous air barrier and insulation layer. Also, it's becoming a bigger trend. A lot of homes you find tray ceilings and you find those drop soffits or those drop ceilings and those soffits within the rooms, so it's easier to put your ducts within them. Another approach is using conditioned basements and crawl spaces. By bringing these spaces inside the thermal envelope, meaning you're conditioning the basements or you're conditioning those crawl spaces, the ducts can be installed without being exposed to extreme temperatures in those areas, which will help improve the efficiency and the performance of the system. And coordination is also a key part of making these strategies successful. Duct layout really should be planned early on in the planning process, and it should be coordinated with framing, structural elements, and finish work to avoid conflicts in the field. When everybody's coordinating and talking together, it does help for better planning. So the image that I have there that I'm showing, this is an example of a soffit detail where the duct is fully enclosed within the conditioned space with insulation and air sealing maintained around it. That's a good example of how proper design and coordination can keep ducts inside the envelope. And as designers, a lot of designers, architects are putting them inside homes as well. So taking all of these approaches into consideration helps reduce the energy loss, it helps simplify the code compliance, and it improves the system performance. So focusing on the importance of integrating ductwork early in the design process, here, one of the biggest benefits is improved coordination among the trades. When all your HVAC framing and design teams are all aligned, it helps reduce conflicts in the field. So early layout planning it also helps with clash detection. By identifying where ducts will run ahead of time, we can avoid issues with structural members, plumbing, or electrical systems that often can cause changes during the construction. Another key tool is the use of 3D modeling and BIM. So these tools allow teams to visualize duct routing within the building envelope, and it helps make adjustments before construction begins, which can save time and costs. So the image that I put on here, speaking about designing early, this is an example of ductwork that can be it's integrated within a truss system here. You can also get it integrated in a floor system, possibly too. So that's keeping all of your ductwork inside that conditioned space. You're not dropping any ceilings or building any soffits. You're putting it up into the truss as well. So, as I stated before, just early planning, it leads to better performance, easier installation, and improved code compliance as well for the system. As we continue here, some advanced placement strategies. The goal is to keep ductwork inside the conditioned space whenever possible. One effective approach is using unvented attics or conditioned roof assemblies, which bring the ducts inside the thermal envelope and reduces that energy loss. To achieve this, we typically use spray foam or rigid board insulation to create a continuous air and thermal barrier around that duct system. But with these strategies, moisture management becomes critical. Proper air sealing and vapor control are key to protecting both the duct system and the building itself. So overall, these approaches improve the duct performance, but they require careful design and installation to work effectively. So now looking ahead, some modern system strategies. Some approaches to this is the first one here is ducted mini splits. They can be very effective solutions, especially in tight homes and smaller load conditions, which are becoming more common here in Pennsylvania as well. One of their biggest advantages is how well they pair with designs that keep ductwork inside the building thermal envelope. Because these systems use shorter, smaller duct runs, it's much easier to route them through conditioned spaces like drop ceilings or soffits or conditioned attics. This helps reduce energy losses, it improves overall system efficiency, and it can make it easier to meet duct leakage and performance requirements. From a design standpoint, it's still critical to pay attention to static pressure and layout. These systems are more sensitive to poor duct design, so proper sizing, short runs, and thoughtful register placements are extremely important and they are key to the system. So overall, a ducted mini split it can be a great fit, especially when the goal is to keep the ductwork inside the conditioned space, but they require careful coordination during design and installation to get their full benefits. Another option is low profile and slim duct systems, which are especially useful when we're trying to keep ductwork within the building thermal envelope. In modular and multifamily construction, space is often limited. And so with that, these compact systems allow ductwork to be routed through drop ceiling soffits or interior chases without compromising the headroom or the design of it. These systems often use plenum or manifold style distribution, which reduces the amount of ductwork needed and makes it easier to keep runs short and fully inside the conditioned space, helping to minimize energy loss as well. Another advantage is the ability to integrate ventilation systems such as ERVs or HRVs directly into the duct layout. When everything is located within the envelope, it improves that overall efficiency and system performance. Some newer and more flexible approaches to HVAC system design is first we have the combining of ducted and ductless systems. That's becoming more common. For example, a home may use a central ducted system for main living areas, and then it uses ductless mini splits for additions, bonus rooms, or hard to condition spaces or hard to reach spaces. This can reduce the need for extensive ductwork and improve the efficiency of the system. Second, we're seeing more compact mechanical rooms and equipment closets. Placing equipment and ducts closer to or inside the conditioned space, that helps to reduce energy loss and it can simplify the code compliance as well. And then lastly here, many of these approaches are being used in retrofits. In existing homes, especially older homes in Pennsylvania, which we have a huge abundance of, running new ductwork inside that envelope can be difficult. Ductless systems or hybrid designs offer practical solutions to improve the comfort, the efficiency uh, of the system, and not create major structural changes as well. So overall here, hybrid and innovative designs provide flexibility, especially when you're looking at retrofit situations while they're also helping to keep systems inside the envelope and improving that overall performance, which is important. So, looking at cost and performance, specifically in relation to duct locations, inside versus outside the building thermal envelope, when ducts are located in outside the envelope, such as in attics or crawl spaces, any leakage or heat loss directly impacts the system efficiency. Even small leaks can result in significant energy loss, which increases operating costs over time. When you bring those ducts inside the thermal envelope, that may increase upfront costs slightly. There might be a little bit more that you have to do due to the design coordination or the soffits or drop ceilings, but and at the end of the day, it can significantly reduce those losses. This helps systems perform closer to their intended efficiency, and it makes it easier to meet those code requirements regarding which compliance path that you're following as well, especially under the performance or the ERI methods. So, from a comfort standpoint, ducts inside the envelope deliver air that stays closer to the intended temperature, improving the consistency from room to room and reducing drafts. It also contributes to quieter operations since the system doesn't have to work as hard to overcome those losses. In and in terms of incentives, looking at that, many programs, particularly those supporting high efficiency heat pumps and improved building envelopes, align well with the strategy. Better duct performance can directly support eligibility for rebates and compliance credits as well. So, overall, looking at all of it, locating ductwork inside the building thermal envelope, it's not just a best practice, it's a strategy that improves efficiency. It supports your code compliance. It enhances that comfort, and it can also provide better long-term value as well. Now, looking ahead, I found there's two case studies that I want to look at. The first one here, this is a real-world case study from the Building Science Corporation. It's titled Duct Dynasty. This study does a great job of illustrating how something as simple as duct location can have a major impact on overall building performance. So as we go through the next couple slides, it's going to compare two common approaches, ducts located outside, which is the common theme of this webinar that we've been talking about today. Ducts located outside that thermal envelope versus ducts brought inside, and evaluates how each affects energy efficiency, system performance, and that long-term durability. So let's start here by looking at what is most commonly done in the field and the problems that result from that approach. In many homes, especially in our climate here in Pennsylvania, it's very common to see ductwork located in vented attics completely outside the building thermal envelope. From a construction standpoint, this is often done for convenience and accessibility. But from a performance standpoint, it creates several challenges. These ducts are now exposed to extreme temperatures, very hot in the summer and very cold in the winter, which leads to significant energy loss. As a result, the HVAC system has to run longer and work harder to maintain interior conditions, increasing both energy use and system wear. What's important to understand is that even if the ducts are insulated, they are still outside the controlled environment of that home. So the next question becomes, why does this create such a significant impact on performance? So from a building science perspective, ducts that are located outside the envelope behave differently than those that are inside. One way to think about it is that ducts in unconditioned spaces, essentially they act like radiators. They're constantly gaining or losing heat to their surrounding areas. In addition, duct leakage becomes a much bigger issue. When ducts leak in an attic, they can pull in hot, humid, or cold air from that space and introduce it directly into the system. This also creates pressure imbalances within the home, which can drive unwanted air infiltration through the building enclosure itself. Beyond performance, there are also durability concerns. When warm, humid air contacts cooler duct surfaces, condensation can occur. This is that building science perspective that I talked about earlier. And what that does is that increases the risk of moisture related issues over time. So that's never a good thing. We don't want to have moisture being created in our buildings. That can cause mold. If we take those ducts and or if the ducts outside the envelope create these challenges, the next step is to look at what is a better approach? What's the better approach? What does it look like? So in this case study, that's what they look like. That's what they looked at here is the solution. So the study shows that one of the most effective strategies is to bring that ductwork inside the building's air barrier and thermal boundary. That can be done in a few different ways. They can use conditioned attics, so they can condition those attics. They can use interior chases, they're building interior chases, or integrating duct pathways into the design early in the project if it's a new build. The key here is coordination. When HVAC design is considered alongside framing and enclosure design from the beginning, it becomes much easier to keep those ducts inside the envelope. There are also several practical design approaches, such as drop ceilings or soffits or even unvented attic assemblies that can help make this possible. My picture that I have there, that shows a drop ceiling or a soffit in the room that could be built for running. It's like a chase to run your HVAC ductwork through. So another important consideration is your duct, or one of the most important considerations is duct layout. The more compact system with shorter runs improve efficiency, and they're easier to keep within the conditioned space as well. So let's look at the results in the code compliance from this case study. When these strategies are applied, we start to see measurable improvements in performance and code compliance. When those ducts are brought inside the thermal envelope, the performance improvements are significant. Energy losses are reduced because the ducts are no longer exposed to extreme conditions, and overall comfort improves due to more consistent temperatures throughout the home. This also reduces the load on the HVAC system itself, which can lead to better efficiency and potentially smaller equipment sizing too. From a code perspective, this approach aligns well with both the IECC and the Pennsylvania UCC compliance paths. In some cases, when ducts and air handlers are fully within the conditioned space, duct leakage testing requirements may be reduced or even eliminated, as I stated earlier in the webinar. It also makes it easier to meet performance-based metrics like ERI targets. So this case study really reinforces the idea that duct location is not just a mechanical decision, it's a building design decision that impacts the entire system in a whole. Moving along, another case study. Here's another one that I looked at. This one was from the U.S. Department of Energy's Building America program. It focuses on high performance duct systems located within conditioned space. This study looks at practical field testing strategies for reducing duct losses and improving overall HVAC efficiency. It also reinforces many of the concepts we just discussed, but from a measured performance standpoint. The goal here is to show how thoughtful design and placement of ductwork, specifically keeping it inside the building envelope, can significantly improve energy performance, comfort, and that long-term durability. So as I go through these next couple slides, think about how these strategies can be incorporated early in the design rather than trying to correct the issues later in construction. Let's start by looking at the overall goals of the project and the core strategy used to achieve them. At its core, the project goal is fairly straightforward: to improve the HVAC efficiency by reducing duct losses. And the most effective way to do that is by keeping those ducts within the building's thermal envelope, where they are protected from extreme temperatures. The core strategy focuses on locating both the ductwork and the air handler inside the conditioned space and aligning those systems with the air barrier and insulation boundary. This alignment is critical. It ensures that the ducts are operating within the same controlled environment as the living space, rather than fighting against it. So once that strategy is established, the next step is understanding how to actually implement it in the real world construction. There are several practical ways to bring this strategy into the design. Common approaches include using drop soffits or interior chases to route that ductwork within the conditioned space. Conditioned or unvented attic assemblies are another effective option, particularly in homes where attic space is being utilized for mechanical systems. Another key factor is keeping duct layouts compact, keeping those shorter runs. That helps reduce losses and improves the system efficiency as well. And just as important as coordination, HVAC design needs to be considered early alongside framing and enclosure design to make these approaches feasible. So when ducts must remain in the attic spaces, you have no other area, alternative approaches can be used, such as encapsulating the ducts with spray foam or burying them in insulation, but these require careful detailing to perform that correctly. So just be careful with it. When those strategies are applied properly, we start to see measurable improvements in system performance. The results from this study clearly show the benefits of bringing ducts inside the envelope. Duct leakage to the exterior is significantly reduced, meaning more of the conditioned air actually reaches those living spaces. Airflow delivery improves, and the temperatures throughout the home become more consistent, which directly impacts occupant comfort as well. From an energy standpoint, heating and cooling loads are reduced, and the system doesn't need to run as long to maintain those set points. All of this contributes to improved overall HVAC efficiency and better system performance. Continuing on here, beyond the performance, there are also important long-term durability and code compliance benefits to consider. From a durability standpoint, keeping ducts inside the conditioned space reduces the risk of the condensation forming on duct surfaces. It also helps prevent, or which can also help prevent moisture-related issues over time. It also contributes to better overall roof and building assembly performance, particularly when the ducts are no longer exposed to those extreme attic conditions. In terms of reliability, the system tends to perform more consistently and it experiences less strain. From a code perspective, this approach aligns well with the code requirements, particularly under the N1103 for duct systems. It can also support Pennsylvania alternative compliance paths and in some cases simplify and reduce duct leakage testing requirements when the system is fully inside that envelope. So overall, this case study reinforces that duct location is a critical design decision, one that impacts not just efficiency, but comfort, durability, and code compliance as well. So as I wrap up here, some key takeaways: duct location matters. Keeping ducts inside the thermal envelope, it does improve the efficiency, it improves the comfort, and it improves the overall system performance. It starts with proper design and early coordination, and it's carried through with quality installation, sealing, and insulation. From a code perspective, compliance paths require verified performance through testing, not just meeting minimum requirements. And finally, advanced strategies like conditioned attics and compact systems make it practical to keep those ducts inside the envelope. When all of these systems come together, or all of these come together, we get better performance, better comfort, and more durability within our homes. So that's why it makes it more important just to bring those ducts inside the thermal envelope.